Hi, welcome back to video class 5. And in the last previous video class, we have discussed 3-bar truss problems, and again similar type of problems we are going to solve in this video class. And in this video class, I have taken two problems regarding 3-bar truss members. And in this video class, I have not done completely step by step here. Just I am going to give hints for these two problems, and you need to solve these two problems, and these two problems will be considered as a exercise problems regarding truss concept. Because I'm going to give only hints, because the procedure will be common again. Okay, wherever you will going to get different things till now what I have not done, for those things I'm going to give hints for these two problems. Okay, just you look at the problem number 4. See, if you see the figure, see this type of problems already was solved in last previous video class. Okay, and you are going to come across two slight changes with respect to last problem what I have done in the last video class. Just to look at the problem statement now. Consider the 3-bar truss as shown in figure. Determine the nodal displacement and stresses in each member. Okay, this is the problem statement. Along with that, they have given figure also. And from this statement, you are supposed to calculate nodal displacement for the structure along with how much stress that is going to be induced in each member. And from the figure we can easily see that they are given three elements along with three nodes are there. Okay, and along with that he has given Young's modulus will be common for all the members, that is 200 gigapascal, and area also he has given for each members. The area for the first element is 1500 mm square, area for the second and third will be 2000 mm square. Okay, and just to observe node 1 and node 2, that is the boundary conditions, they are not the same here. Node 1, it is completely constrained, that is there is no movement along x, y, z, whereas for node 2 condition is different. They are given rulers along x axis. It means that exactly at node 2 we have a x movement, an x axis certain movement will be there. I should not take it as a 0 here, and exactly at node 2 in y direction you have to take 0 because there is no movement along y axis. Okay, see, I told just now, I told you are going to get slight two differences we're going to come across with the last problem with this problem. What are those two slight differences? Just exactly at node 2 for the previous problem there is no load is acting here. Yes or no? Here exactly at node 2 load is acting how much, that is 15 kilonewton acting along x axis, that too in positive direction. Okay, for this I am going to take as a F3. Yes or no? F1, F2 will be meant will going to representing at node 1, and for node 2 it is F3, F4, and similarly for node 3 it is F5, F6. Since it is acting along x axis, my loading condition I have to take as F3, that to positive value I have to take. Okay. Similarly, just you look into the problem number, node 3. Exactly, if you see the last previous problem what I did in the last class, the load with same magnitude, that is 150 kilonewton, that is acting exactly 90 degree to the node 3. But in this problem, the loading condition is acting at an angle of 45 degree. Okay, if these problems are given, how to overcome this problem now? See, whenever the load is acting at an angle with respect to certain axis, then you have to go for resolution of the forces. This concept you might have already done in physics in first year concepts. Okay, whenever the force is acting at an angle, this can be resolved into two vertical components, that is one along x axis, another along y axis. And for x axis, the resolution will be done as f into cos theta. Here theta is how much? 45, nothing but f into cos theta. F is given already, that is 150 kilonewton into cos 45, that is for x axis. Similarly for y axis, that is f into sin theta. F is already given, that is 150 into sin 45. Okay, we know that the force is acting, total force 150 kilometers is acting in downward direction. For these two, for x and y, you need to take as a negative. Okay, just once you drawn FE model, and exactly at node 3 I need to draw again Q5 Q6. exactly at node 1 q1 q2, for exactly at node 2 q3 q4, exactly at node 3 you need to represent q5 q6 similar along with f5 f6. Nothing but here both f5 and f6 are going to get negative values along with q5 q6. These two are called nodal displacement values at node 3 along x and along y, and f5 f6 just now I got resolved now. f5 nothing but f into cos 45, f6 nothing but it is f into sin 45. The both the values will be in negative value because the total force is acting along downward direction. Okay, so that's what the difference you're going to come across with respect to last problem and this problem. So here, just to observe here, load is acting at node 3 and is resolved into two components, that is f5 along x-axis, f into cos 45. Negative value I have taken because it is acting in downward direction. If you do it, you're going to get 1,06,066 Newton for both the f5 and f6 with negative value. You understood? See here, I told just I have not done step by step. Directly I have taken global stiffness matrix because every magnitude is common with respect to last previous problem. I have not done K1, K2, K3. Already I have taken directly global stiffness matrix here. And similarly I want to create my global force vector. This is what the difference you're going to find with the last previous problem and along with this problem. And F1 there, F1, F2, F3, F4, okay, everything will be 0 there. And here f1 will be 0, f2 will be 0, whereas f3 will be here they are given, that is 15 kilonewton. Understood or not? And f4 will be 0 obviously. And f5 now you just know your result, that is f into cos 45, and for f6 just now you result f into sin 45. If you do it, you will get same value, that is 1,06,066 Newton. Whereas for the last previous problem, you don't have f1, f2, f3, f4, f5 all will be taken as a 0. Only f6 you have taken as a value with negative, that is acting in downward direction. See, this is what the difference you are going to find with this problem and the last problem which I have done in the last previous class. Now you apply boundary conditions now. Same thing you have to apply boundary condition. Just to observe the figure, the node 1 is completely constrained. Nothing but q1 and q2 will be completely 0. Now here, since it has a rolling condition, I should not take q3 will be 0 because q3 nothing but it is going to have a certain movement along x-axis. Now I should take q4 is a 0. Now you know apply boundary condition. q1, q2, q4 is equal to 0. Nothing but in the global stiffness matrix or equation of equilibrium, you need to eliminate complete first row, first column, second row, second column, along with fourth row, fourth column in equation of equilibrium equation. So after applying boundary condition, the remaining terms are as it is. You got, that is 10 to the power of 5 in the matrix of 7.285, 3.53, 3.53, minus 3.53, 7.0710, 3.530, 7.013. Remaining will be after eliminating the remaining displacement values are Q3, Q5, Q6, and forces are 15,000 along with minus 1,06,066, as I have written in terms of 10 to the power of multiples. Okay, just after calculating using simplification, using calc you can easily get it. After simplification, the values you got is q3 is equal to 0.04 mm and q5 is equal to minus 0.13, q6 is equal to minus 0.17 mm. Okay, again same the stress formulas will be for each member. Sigma 1 is equal to E1 by EL L1, because nothing but for particular element I am representing E1. For sigma 2 you have to represent E2 L2 like that, minus L minus M Lm with respect to the global the nodal displacement values for the elements, that is q1, q2, q3, q4, because first element is made up of two nodes, first node and second node. Here each node having 2 degrees of freedom. For one element, minimum of 4 degrees of freedom will be come into picture. Young's modulus here is given 2 into 10 to the power of 5 divided by length is for the first element is 800 mm, and here L you got it similarly, you got it for L is equal to, you got the value of 1. Since it is positive here, the formula is negative, you have to represent negative. 0, L, again L is 1, M is 0 and M is 0 here. Same, you put the value, you will going to get the values here. Q1, Q2 will be 0, that is completely fixed. And you got, just now you got the value of Q3 0.04, Q4 will be 0. By solving, you are going to get the value of sigma 1 is equal to 10 Newton per mm square. Similarly for sigma 2, if you calculate, you get 0. Similar for sigma 3, it is minus 75 Newton per mm square. Okay, see, this is the this is how we are going to solve the problems. Okay, same problem with little bit changes we are going to come across. That is that exactly at node 3, in the last previous problem, the load is acting exactly perpendicular to the node 3, whereas in this video, in this class, in this problem, the load is acting exactly 45 degree to the node 3. Okay, this is the slight difference we're going to come across. And one more difference is there, in the last previous video class, exactly at node 2 there is no load is acting, but here load is acting, that is in positive direction along x-axis, that is 15 kilonewton. Okay, this is one of the important problem, and this problem also I will going to solve in ANSYS lab also. Okay, next we go for next problem. Okay, here also this is a 3-bar truss member. Okay, for this again, just I'm going to read the problem statement here. For the truss as shown in figure, determine the horizontal vertical components, nothing but respective nodes. You are representing no Q1, Q2, Q3, Q4, all those are called horizontal and vertical displacement values at the nodes, and stresses in each element, and Young's modulus for each element is as given 201 gigapascal, and area for each element will be as given 4 into 10 to the power minus 4 meter square as given. Okay, here all the terms they are given in terms of meter. And also here in this problem they are given how many nodes are there, 4 nodes are there. Okay, 4 nodes are there along with 3 elements they have given. Okay, for this the difference will be going to come across here when you are going to creating for nodal coordinate data table. Okay, while creating, I told, while creating your nodal coordinate data table, some exactly at some point or some node will be considered as a reference point. Okay, with that reference point we need to fill the nodal coordinate data. Okay, nothing but with reference to that particular point, how far other nodes will going to be situated, that is will going to be filled in this nodal coordinate data. Just how many nodes are there here? From the figure we can came to know that 4 nodes are there. 1, 2, 3, 4 already they have given in the problem. Along with you have to represent now x and y coordinates values. Okay, here I will going to take one as a reference point now. One as a reference point. If you take one as a reference point, for that the coordinates will be 0, 0. Okay, now 2, just you 2 exactly at node 2 already they have mentioned x2 y2, that value will be again x will be 0, y will be at height of 3 meter. Okay, 3 meter will be there again for node 3, just leave it node 3, just you go for node 4 now. Node 4 is situated along, that is represent x4 y4. X4 will be always nothing but x-axis will be at a distance of reference point is 3 meter, y will be, there is no height for that, and that's why I written 0. Now what about node 3 now? x3 y3 they have not given, just we know the length of the element. Understood? For this problem what you have to do is exactly at points here, exactly from the B point I represented B, from that point you draw a line, a straight line that is perpendicular, it means it become perpendicular to the x-axis. Okay, that will be, that height will be y3, and the distance will be exactly where it is intersecting at y-axis from the horizon, it will be x3. Now we are going to solve for x3 and y3. Okay, now let us see exactly acting at 45 degree with respect to vertical line with respect to horizontal line now. Okay, just to assume now it is acting at 45 degree now. Understood? I want y3 value. In order to get y3 value I have to go for sine value. Okay, sine, what is sine value? Sine theta nothing but what? Opposite by hypotenuse. Opposite by hypotenuse. Just sine 45 is equal to opposite, what is the value? y3. I don't know y3 now. divided by hypotenuse value I know, that is 3 meter. Now y3 is equal to what now? Sin 45 into 3. So that's what I have written in nodal coordinate data table. Similarly, you go for, you have to take in such a way that I want now adjacent along with hypotenuse. It means that obviously you have to go for cos theta. Cos theta is nothing but adjacent value divided by hypotenuse. Adjacent. What is adjacent value? That is x3. Cos 45 is equal to x3 divided by hypotenuse. What is the hypotenuse value? 3. It means that x3 is equal to cos 45 into 3. If you do it, again you are going to get 2.121, 2.121 for both x3 and y3 value. See, this is what some different problem we're going to come across in this truss problems. Okay. Now once you got the x3 and y3 values, it is easy for filling your nodal coordinate data. Okay, and again it is similar procedure you need to follow for that. Again directly I have taken global stiffness matrix now. Understood? See here, how many elements are there here? 3 elements. How many nodes are there here? 4 nodes. 1, 2, 3, 4. It means that my global stiffness matrix will be how much? That is 4 nodes into 2 degrees at each node. That is total how much? 8. My global stiffness matrix will be of the size of 8 by 8. Okay, since it is a trusses, and in trusses each node having 2 degrees of freedom, because it's going to consider as a, your planar trusses will be considered as a 2-dimensional body. It means that each node is having 2 degrees of freedom. How many nodes are there? 4. 4 into 2 it equal to 8. Nothing but my global stiffness matrix will be of the size of 8 by 8. That's what I have created here. Understood? Now apply boundary condition. Just you observe the figure here. It is easy for you because everything is completely constrained here. Node 1, there is no fixed. That's what the, see, just while for creation of few model, just you create that at node 1, q1, q2. These are the two nodal displacement values at node 1 along x and y, and also exactly at node 1 your forces are acting here. Forces are loading conditions are acting, one along y, one along x direction. Okay, that means that F1 and F2 has given. F1 is acting negative value, that is minus 10 kilonewton you have to take. For F2 you have to take again negative because acting downward direction, that is F2 is nothing but minus 20 kilonewton. Similarly, where is my node 2? Exactly at the top, which is at a 3 meter height from the origin, that is 2. There x to y to they are represented, and there I have to represented q3, q4 and comma f3, f4, because q3, q4 will be 0 because it is completely constrained, along with there is no force, that will also taken as a 0 for that. Similarly comes to now node 3. Node 3 there also represent now 5, 6. Now you have to represent 5, 6, q5, q6. Nodal displacement values at node 3. With respect to x and y, you have to represent again f5, f6. There is no f5, f6, you have to take as a 0, and also for nodal values also take 0 for that. Now you come for node 4. There you have to take q7, q8. That value you have to take 0 because it is completely constrained, and f7, f8 also you have to take 0 because there is no force acting on that. Okay, so nothing but here you need to calculate total 8 cross you're going to calculate, that is global stiffness value I have taken now. And okay, this is my global stiffness matrix of size 8 cross 8. See here how many elements are there? 3 elements are there, yes or no? And we need to calculate here 3 element of stiffness matrix first. And before going for that, one more thing you have to do is element connectivity data there. For element connectivity data, I'm going to explain now how you have to get is element, how many elements are there? 1, 2, 3. And for first element here, which one is going to take initial, which one is going to take initial. First node, it is, say first element, it is made up of 2 nodes, node 1, node 2. I will take initial as a 1, final as a 2 here. Similarly for second element, I will take initial as a 1, final as a 3. Similarly for third element, initial as a 1, final as a 4 now. And effective length is common for all the elements. He has given 3 meter, and direction of collision you need to calculate. Okay, that is similar. The formula is L is equal to again x final load minus x initial load divided by effective length. For M, is equal to y final load minus y initial load divided by effective length. L is always corresponding to x coordinate, m is always corresponding to y coordinate. Okay. Now for creation of finite element model for the first element, the formula is always a formula, that is AE by L in the matrix of L square ml minus L square minus ml, ml m square minus ml minus m square minus L square minus ml, L square ml minus ml minus m square ml m square. See, this is what inside the elements of your matrix. And while creation of your elemental stiffness matrix for the first element, at the top you have to represent 1 2 3 4, 1 2 3 4. Whereas for second element, again it starts with again 1 2 5 6. Sir, because you are taken initial node as a common for all the elements. For all three elements, initial node is 1. It always starts with 1 2. For elemental stiffness matrix of the first element, it starts with 1 2 3 4. Similarly for second element, 1 2 5 6. Similarly for third element, it starts with 1 2 7 8. Now it has become, now total your global stiffness matrix become of the size of 1 to 8, nothing but 8 by 8. You got the idea or not? Okay. Understood or not? Now my global stiffness matrix of the size of 8 cross 8. So once you created a global stiffness matrix 8 cross 8, again go for your boundary conditions. Okay, that boundary condition is very easy because everything is fixed. What are the values you're going to get cancelled is Q3, Q4 along with Q5, Q6, Q7, Q8. Everything going to be get cancelled, and these things will going to be eliminated in equation of equilibrium, and the remaining terms will be, I have written here. Okay, if you get simplification, you're going to solve, that is going to be, you will get the values of, and Q1, Q2 you will going to get the values. Those Q1 is nothing but minus 9.37 10 to the power minus 5 meter, and Q2 is equal to minus 4.66 in 10 to the power minus 4 meter. And global stiffness matrix force vector I have represented. Already I told also, that is a F1 and F2 I have given, that is F1 is minus 10 in 10 to the power 3, and for F2 it is given in downward direction, that's why it is minus 20 kilonewton. Okay, see, this is what we are going to do it in this class. Again, one more thing here, how to calculate stresses also there. Stress is nothing but you have a direct formula, that is E by L is equal to minus L minus M Lm with respect to how many global displacement vectors for the first, always for elements it will be 4, because here one element is made up of two nodes. Here two nodes at each node having 2 degrees of freedom. Now each element is representing 4 degrees of freedom. That's what I represent Q1, Q2, Q3, Q4. Q1, Q2 just now we have calculated, and Q3, Q4 will be 0. After simplification, we will going to get 31.22 into the power of 6 Newton per meters, Newton per, so attack meter. Similarly for Newton per meter square. Sorry, I made a mistake here. You have to take Newton per meter square, not mm square. That is just to make it correction there. Okay, 31.22 into 10 to the power of 6 Newton per meter square. Similarly, you need to calculate for other elements also, that is sigma 2 and sigma 3. See, these are the problems we're going to come across. See, this is a different problem compared to other problems what I have done for so far. Okay, just here you need to give concentration is that only for x3 y3 values, and also be careful that which one you have to take initial. For all the elements, my initial node will be 1, because all the elements starts with node 1 only. Okay, for example here node 1 as initial, for the first element final is node 2. Similarly for second element, initial is 1, and for final is third node. Similarly for third element, it is 1 as initial and 4th as a final. Like that you have to do it. Understood? So this is how you are going to come across some of the difficulties in some other problems here. Okay, just I have given hints wherever you are going to just concentrate on these two problems. If you have any difficulties arises among these two problems, just to give comment on Google Classroom, so that I am going to rectify in the next previous video class. Okay, thank you.